There.
Okay, fair enough. Okay, so thank you all for coming, and I'm going to hand it over to Natalia, Oliver, and Cameron to put together the presentation. And there we go. Pin us. Okay. All right, take it away, guys.
Thanks, Ben. So as Ben said, we're part of the UMass Energy Corps. My name's Cam.
Natalia.
Hello. So some of the things that we were looking into for Pelham Elementary that came up where there was a lot of canceled school days due to high temperatures and no cooling system. It's dependent on school choice students. There's a limited summer occupancy, and the current heating and ventilation systems are roughly 25 years old and are oil fueled. Some of the town goals were to have a comprehensive plan incorporating replacement of the current equipment, specifically electrification and the addition of cooling. We want to get off fossil fuels and have a better idea of upcoming costs and potential funding sources, and ideally meeting the Green Communities Baseline and Climate Relief Program. So just a quick overview of the recommendations that we had planned were for ventilation, to use enthalpy recovery, to precondition the ventilation air. We want to switch to heat pumps with a direct expansion coil. In the dedicated outdoor air system, we want to precondition that air. We want to install new ducts where possible, but use the existing ones that we have there and reroute the exhaust for recovery. And we want the hot water coil to be used for extreme low temperature conditions. For air sealing, we want to seal the roof and wall interface. For heating and cooling, we want to convert the existing unit ventilators to fan coil units. We want to remain having the cooling supplied by DOAS and the boiler replaced by air to water heat pumps. And for the rooftop gym unit, we want to replace that with a dedicated outdoor air system, but with hot water coil sized for space conditioning. And just use a replacement or de-stratification vents. So for air sealing, Rupert was kind enough to depressurize or pressurize the building, I should say. And you can see the red arrows is where we're thinking of sealing it off. And in the thermographic images, you can see the red is where there's some leakage. So sealing that off would help a lot. For ventilation, the current system, the classrooms currently use unit ventilators and exhaust fans with no heat recovery. And the rooftop units for offices and the gymnasium with mixed air dampers have the direct expansion coil, hot water coil, respectively, again, with no heat recovery. So we propose implementing enthalpy recovery to decrease loads in the hydronic system. And the rooftop units will precondition that fresh air with the integrated heat pump, and the supply will be 100% outdoor air. And so as I was saying up top here, we'll have that enthalpy recovery, the fresh air. It'll go through those fans back behind it and then hit those coils. And the second image shows the heat.
Okay, so when it comes to heating, the current system utilizes unit vents, fin tubes, fan coils, and cavity unit heaters, which have a high temperature hot water supply from the oil boiler, and also the rooftop unit in the gymnasium has a hot water boiler to heat that space. What we're supposed to do is to use a air to water heat pump with modular chillers to supply a majority of the heating loads and to supply water temperature that can be decreased using all the existing piping. We also propose to use a direct open air system unit with integrated direct expansion coils to condition the air supply. As you can see here, this is a graph of the coefficient performance of the heating pump in heating mode. And as the outdoor temperature increases, the coefficient performance increases as well, as it's easier to heat the air. And we're using an RBI air source as the design for that. When it comes to cooling, a quick explanation of what cooling loads are. Cooling can be divided into sensible loads and latent loads. Sensible loads, which account for about 60% of the load, is encountered through like physical experience, such as sunlight, heat generated from occupants, heat from lighting fixtures and appliances, and heat conducted through the building envelope, like the walls, ceilings, and floors. The secondary load is the latent loads, which is about 40%, and it's basically has to do with the humidity, and it accounts for occupant respiration, infiltration of humid outdoor air, humidifiers, and other sources of moisture like steam from cooking. To address the sensible cooling loads, the current system only cools the office with a rooftop air-cooled condensing unit. And there was cooling in the computer room, but it no longer is in use. What we're proposing to do is to run above dew point chilled water through the fan coils to address the cooling loads and have the DOAS units with the TX coils for the preconditions of fire. To address the latent cooling, the current system uses the unit ventilators, which run during the summer with assumed 100% outdoor air in economizer mode, which allows for the temperature to be decreased during the daytime, but all the comfort levels are not always achieved. What we're proposing to do is to transition ventilation entirely to the rooftop units and have the air conditioning handled through the DOS. The DOS units will handle all the cooling through gas reheat handles. The cooling loads will be handled through. Similar to heating, this graph shows the cooling efficiency of the heat pump in cooling mode. And as the temperature increases, the coefficient decreases. It's harder to cool the air than heat it, and it's also based off the RBI. This graph here shows the frequency of the temperatures we experience in relation to the coefficient performance and the hot water temperature. So as the temperatures decrease, the hot water temperature rises. And as temperature also decreases, the coefficient of performance decreases.
All right, so now we're going to talk a little bit about the new distribution ductwork system that we was putting in. So as mentioned, the plan is to block off all those unit ventilators that were previously providing the supply air for those classrooms. So every room, the classrooms, and the offices that were ventilated with those units are going to have new supply ducts running to them in order to make up for that. But in those spaces that have the exhaust fans, we're able to reuse that return ductwork. And instead of having that air get directly exhausted through the exhaust fans in the roof, we propose just adding runs of return duct to go up to those rooftop units so that we can, as pictured before, use enthalpy recovery where those two air streams cross each other, and then you get better efficiency for your ventilation. Oh yeah, and the DOS units also have variable speed fans and compressors. So instead of running at 100% on, 100% off, you can run at quarter, 50% efficiency, which is better for energy saving. Our gym rooftop unit is a little bit different from the rest of the DOAS units because, as mentioned, that space is entirely heated and will be cooled by that rooftop unit. There's no hydronic system in there. So that unit will have to have a hot water coil that is sized for conditioning that space. And that hot water is going to be supplied by the air to water heat pump. So we propose adding that space also will probably have to have either higher velocity supply diffusers or destratification fans in order to get better circulation of the air in that space. And again, we're going to be sealing off the exhaust fan and just rerouting where there's already return ductwork going up to the roof for the mixed air damper. That will just serve as 100% exhaust air. So this is a visualization of what the new supply ductwork might look like. The DOS unit one, as pictured there, is in the location of where there's already an existing unit ventilator. There's a little bit of supply ductwork that's already there. In yellow is the new supply ductwork, so some of that is overlaid with ductwork that already exists. There's a couple of supply diffusers already in the hallways there. But then the runs going to the classrooms, that will all be new ductwork. And then in the green, that's the current exhaust ductwork. And the exhaust fans pictured in red, those are where they're getting sealed off. And then as you can see, the green lines, the return ducts are gonna run back up to the roof where they meet the DOS unit up there. The nice thing about this system is that because we're not, well, besides the gym, we're not using the ventilation air to entirely heat or cool those spaces. We're able to use smaller ductwork, which means that we're not using ductwork of this size to bring in enormous amounts of air. So we can use relatively small ductwork, especially as we get further down the branch lines, so that it's not a super invasive process. And then it would just be typical ceiling diffusers that would go into your drop ceiling, like how you would typically see in an office. Then it's pictured in the gym. Sorry. We already have supply ductwork that's there, and so as mentioned, that can just remain the same. Besides maybe adding some new diffusers or fans in it. So for the south side of the building, pretty similar situation. We have a few different zones, which is nice, so that if we were to say in the summertime have a summer program that maybe only runs in one of the classrooms or in there's people in the offices, you're able to zone the building so that you're not providing air conditioning for the entire space. The CFMs, so the 3,000 and the 2,000, those ventilation rates were calculated just based on the exhaust fans that currently serve those spaces. So they can be different sizes depending on the needs of those classrooms and offices. Again, in red, that's where all of the unit ventilators we propose to seal off. That would just look like, pulling off the louver, putting in a piece of foam board, sheet metal, and then air sealing around, putting the louver back. And then again, new supply and return ductwork. And it's not pictured in this drawing, but again, the hydronic system really doesn't get touched at all. We can use all of that existing piping that runs the unit ventilators, especially because even the chilled water, which is above dew point, it means that we don't have to install any sort of condensate system. So that's not serving any latent cooling loads. You're able to just use all that piping with no condensate issues. So this shows the projected savings that we would get from this new system upgrade. This also includes the additional cost that we would incur from adding cooling, because obviously that would bump up your electricity use a bit. And these numbers were calculated based on local weather data and a regression model based on the equipment that we mentioned. So it's about a 15% savings if we were to only do some of those envelope upgrades, as well as adding the rooftop units. And then with the air to water heat pumps, that's about 80% savings. So that's with almost full electrification. It comes out to about $16,000 a year and a 50% reduction approximately in CO2 emissions. So this is a ballpark estimate. The numbers on this sort of thing are pretty hard to predict. but this just gives you an idea of what some of this equipment might cost between the rooftop units, the air sealing, and some of the new ductwork, as well as the air heat pumps. So we wanted to highlight the fact that not all benefits are quantitative. You can see the savings that you'll get, but there's also improved air quality. We're controlling the supplier that we're bringing into the building. So it means that we're able to add filters, which would reduce allergens, pollutants, improve the indoor air quality. We also have, controlled cooling throughout all of the classrooms, which previously didn't have it, as well as in the gym. And there's been studies showing that higher ventilation rates as well as cooling can lead to improved test scores. Um, there's also the benefit of reduced noise because we're not necessarily having those unit ventilators with fans running all the time at full speed. The supply fans are going to be on the roof as well as the compressors. So the air that we're bringing in is coming in at a much lower noise. So as to the order in which these upgrades could happen, the first step would probably be to coordinate the re-roofing, which you had mentioned was already in the plan for the near future. That would include, bringing the roof up to code, probably adding another layer of foam. And then while that's happening, we would propose adding roof curbs and making, holes in the roof basically for where the new ductwork would be coming up through. Um, Step number two would be to, after those rooftop units get placed, convert the unit ventilators to fan coils, which just means sealing off the fresh air intake. And that could be actually done separately because, in the meantime, we could just turn the fresh air dampers off after those rooftop units are placed. Step number three would be adding the air to water heat pumps / modular chillers. That would just be as simple as, having pipes that go to your existing hydronic system with the circulator pumps. And then finally, an extra thing would be to have a indirect coil running from those heat pumps to the domestic hot water tank, which is currently electric resistance. Some other miscellaneous things are the air sealing, which could happen at any time around that, the rim joist air to the roof to wall interface. We propose keeping the oil boiler for backup. And finally, we saw some fluorescent lighting that we recommend switching to LED fixtures. And that's all I have. Any questions?
Yeah, so we'd love to open it up for questions. I guess I'm gonna, something in the chat, I'm going to try and view this second here. I can see everyone. To us. All right, yeah, so do we have any questions or comments, challenges? Thoughts?
You go first, it's your building.
Okay. Do you have an idea of where you might put those air to water heat pumps? Is that rooftop or ground mounted? Is there kind of advantage either way?
Probably ground, because of where the boiler is, you probably want them to basically go through that wall.
Right, so somewhere between the elementary school and the library. Yeah.
Yeah, nice thing is they're not very large, so they don't, they're not very heavy. They don't take up a ton.
In your study, did you get a chance to look at our electric capacity? Do we need to also consider a bigger service for to cover for the heat pumps?
We did not look at that. We didn't, actually, I can't remember why we didn't see it. But shoot, I actually don't even know what your service is.
Yeah, I don't remember either.
Huh. Yeah, that is a potential thing. It may be that you have service at the community center that can be linked there.
I mean, there may be plenty of capacity, because of course, our demand is going down as we change lighting over from incandescent. LED, so there may be sufficient capacity, I just
Yeah,
haven't looked at it yet.
given the things that are no longer functioning, the air conditioning for the former computer room, the air conditioning that is functioning for the office, and the fact that kitchens are going to be high. It suggests potentially we get plenty, both with what's not there, but what was planned.
And we really don't have a full kitchen.
Right, so it's just a scheme.
It's a kitchen, not even that, it's a kitchenette. And we bring, the food is prepared at a kitchen in one of the other schools.
But was it always the case?
I don't know.
Because very often these schools were planned with kitchens. Often the biggest user was actually this steam
Yeah,
heater thing, which is an electric resistant steam heater. So very often that is a thing that, especially if it's not being used, has all the capacity you need. But the short answer is no, we didn't
yeah.
get it.
I guess I worry a bunch about condensation. And so can you talk a little bit about how and where you measure your dew points when you're in cooling mode, and how the system might respond?
Yeah, so you would need to measure dew points inside. Probably in each of the zones. And whatever is the highest dew point is the set point that the chiller has to go to. See, the higher your dew point, the less capacity you have, because you're circulating higher water. Because the DOAS units, so the ventilation units have heat pumps in them, and because they're designed specifically to deal with the latent loads, they should be able to maintain a dew point fairly precisely, or quite precisely. You should be able to maintain that 55-degree dew point, regardless of conditions. So the hot gas reheat component of it is, if all you need is dehumidification, you don't really need a lot of cooling. You actually take that energy that you're going to throw out into the atmosphere and you put it back into the airstream to warm it back up. So you're not losing anything. But as your temperature requirements are going up, and as you have more sensible load in the space, that hot gas reheat works less, and you send cooler, dry air into that space. So as it gets colder, you actually get more sensible capacity out of your ventilation system. Which is why there's kind of this trade-off, and you can always provide sufficient sensible capacity with your water temperature setting.
In an ideal HVAC world, we would control all of our fresh air coming in by running it through the enthalpy energy recovery unit. But in the practical world, kids will be going in and out, doors will be open, folks will open windows. Are there studies about how that affects this kind of a system that you know?
So there are controls and then there are studies. So the controls, if the dew point sensor senses dew point rising, you may find that you're not getting sufficient sensible cooling because the dew point sensor has increased the water temperature to prevent condensation. The number of hours where that's going to be a problem where people are so uncomfortable complaining. Second one, so this is more on the studies. is people have been doing hydronic cooling for what? In this building, not in this room, but in other spaces in this building, we actually have chilled beams. And they basically circulate chilled water that's above dew point. Because if it's below dew point, you start to have rain on your head. The reality is with those chilled beams, they have found that you could actually be below dew point. Having your chilled water average temperature be below dew point. And you can be, you know, the guy's name is Mumia. This is from a bunch of Astro Journal articles back in the 2000 teens. And he tested a bunch of these things, and I'm also trying to convert now to Fahrenheit. But like, so he basically you could be 4 degrees below dew point, and you would start to get condensation, but you didn't get droplets that actually coalesced and formed into droplets that drop. So there's a certain amount of buffer in that, which allows hydronic systems, HVAC systems in general, but hydronic systems in particular are very slow. They send water out, it changes, nothing really changes for a little while, and you know things are very slow to adapt to those conditions, which in this case is a good thing, because everything is kind of just cruising along. So his studies and lots of kind of real world experience show that you can actually get below dew point for a good long time and not cause an but you can see compensation. So yeah, that was that part. The main part is the controls. That you want to stay a few degrees above dew point. Fortunately, if we go back to this doesn't show the humidity part of it, but what it shows us is that if we're talking about the frequently experienced temperatures, like, and this is for a full year, this is not for the school year, right? You know, we're typically in here, which means that our sensible loads are not terribly high, right? We have a lot more kind of effort that has to go into dealing with our latent loads, which is why you're so concerned about compensation. But what that means is that we can probably do almost all the cooling with those ventilation units. They're really doing
They're doing the dehumidification.
They're doing all the dehumidification, which is most of it. And again, they're also providing some sensible cooling because they're delivering air at around 55 degrees. So the net result is like the chiller part is like a little bonus, and it helps for the side of the building that maybe get a lot of sun, or you know might have some sort of high sensible load. But again, especially during the school year, you know, these are the temperatures before. Those are mostly, that's where humidity is much bigger part of it.
And even in the gym where you would probably see the highest latent loads when, you know, it's sweating and breathing a lot. That space doesn't even have a hydronic system in it. So that would be entirely, there's not a concern of condensation to begin with.
Yeah, exactly.
We have the AC system, the old computer lab that's now been repurposed. Has been a headache for us because the refrigerant lines are not well insulated, and there's enough air that gets above the drop ceiling that it can drip on the ceiling and raise a lot of concerns.
Yeah, so one benefit here is these units are unitary. You know, they get craned onto your roof. The heat pump, all the refrigerant, everything is all part of one object. And so you don't have refrigerant to your building. In the case of the gym unit, you do have a hot water coil going to it. But that's really only to supplement, like, so we've sized it for the cooling loads. And as it gets really, really cold outside, the heat pump, the built-in heat pump may not have, probably won't. If you effectively design it, it shouldn't have capacity sufficient at those really low temperatures, but fortunately, the chiller would, or it's like incredibly, still got that oil fire, boiler sitting there. It's
Right, or we had a service in the middle of winter. We got back.
Yeah.
I think you probably already covered this, but I forgot, do you have a sense of how many enthalpy recovery ventilators we use?
Yes.
I understand there's sort of the gym is standalone, and then there's the rest of the space.
Yeah, so we have the one in the gym, like you mentioned, the one for the north side of the building, the few of the classrooms, plus the cafeteria up there.
So one for that whole wing.
Yeah, and that's a high, I believe that's a 4,000 CFM unit, so that's a little bit higher than the two that are in the south half of the building, which are like 2,000 and 3,000. And again, those are all at locations that already have duct penetrations as well as hot water coils that already go there because they supply heating to
To the office suite, yeah.
yeah, so you don't even need to really run a whole lot of piping.
Yeah.
And so with those energy recovery units, enthalpy recovery units sort of define the zones for the building in terms of temperature control?
Well, kind of. So remember in winter or in heating mode, the primary source of heat is still those unit ventilators. It's just that now they're fan coil units, so they can operate with a maximum water temperature of, we calculated
115.
115
Wow.
as the maximum required water temperature.
Because they're not warming up the outside air, they're just recovering what's lost.
Not even recovering. All they're doing is
Just return air within the
Replacing
classroom.
they're just now a fan coil unit, but they're too big
Yeah.
because they don't need to do any outdoor. Right, so that's why that existing system can now do the whole deal. With the usual temperature is gonna be like 90, 95, something like that, which
Your
allows,
preconditioned ventilation air is coming in neutral.
it's coming in neutral, exactly. Or it's possible to bump it up if you needed to, if you needed additional capacity. And this is one where you'd have to fine tune because you've got these two different systems and you're trying to optimize your efficiency. So you could find that at certain temperatures, you're actually better off keeping the water temperature a little low, adding a little heat from the ventilation system to make it work. So there's always fine tuning. So the point that Oliver was making about this unit in particular, that is basically in the location of the current air conditioning unit for the office, is that it can have zone dampers. So that, and because all of these are variable speed pieces of equipment, if you take these two zones off, or all these zones off, whether you're in heating or cooling, those dampers close because somebody said they're not operating. The machine slows itself way down, and you're basically resizing dynamically for the system.
It's like a variable volume system, but zone wise instead of.
Yep, exactly.
At the district.
Exactly. It's each one of these zone. And then in summer, most of the time, you're just cooling the office. And so this whole branch then can be turned off. So it gives you roughly with the hydronic system, every zone is a zone. And you've got really good granular control. Use it. This doesn't take away.
Makes sense. How important do you think it is to time the rooftop work to take advantage of added insulation, or is it just while you're making penetrations and you're sealing the one?
The main concept was, if you're paying people to be up on the roof and remove equipment, let's not pay them to put equipment back up that you don't want. Right? you know,
Coordinated.
try to coordinate it so that you just avoid two contracts or, you know, or two invasive moments. Design, you know, when you're doing your roof design and you realize that this unit that I want has a curb this size, that you build in the curb the right size the first time. It's not that you couldn't do the roof first and then come in and punch a hole. But it would cost you more than doing it in the port.
So correct me if I'm wrong, it sounds like you think we would have the heating and cooling capacity without increasing the insulation of the roof. It's mostly to save money on time.
Yeah, so the energy model that produced that is a regression model. Took your actual energy use and the actual weather you experienced during those Bill Reed moments, you know, during the use, all the electricity used. And we basically built a regression. In most cases, it's linear. In this case, the it's got a slightly different shape. And that model is the basis of this. And then we imposed on it what they call a typical model year, a meteorological year, which is basically, it kind of like takes a bunch of years and it's a standard way of kind of creating a typical year. So that's using your building as it exists. If you do the air sealing that we suggested, you know, that I think the air sealing alone, I've forgotten what it was because here we put it together, but I think it was something like 8% savings of just energy, and we can discuss which type of energy you're putting in depending on whether it's now or in the future. So air sealing does create a benefit. One thing that does, let's say you did the insulation in the roof and the air sealing. One of the things that does is we calculated that you need 115 degrees at design temperature of -5 degrees Fahrenheit. But if we just cut, I don't know, with the air sealing plus the roof insulation that we shouldn't even make a guess at. Let's say we've got it down, we've cut 5 to 10% off. Well, that means that your water temperature, maybe that's 105 degrees. And what that does is, right, that lowers this slope a bit, the water temperature, and the lower the water temperature, the higher the efficiency. So that maybe your seasonal coefficient of performance, instead of being 3.8, maybe it goes all the way up to 4, which is basically competitive with geothermal. So little tweaks in water temperature, which are made possible by insulation, could have that. But everything we sized and all the savings we calculated assumed no roof insulation.
That clarifies that a lot. I guess I have another sort of building document experience. With your energy recovery, you'll have a higher quality filter for dust and pollen and whatnot. With the unit ventilators no longer increasing outside air, you're cutting down on potential dust and mold, etc. The unit ventilators have sort of so-so filters in them, average for the period. Since they don't need to move as much air or temperature, is it worth thinking about increasing the filtration so that on the room by room level, we also are pulling more dust and whatnot out of the air?
Exactly. So there are kind of there's trade-offs, and you could judge these in real time, you know, like you could actually experiment, right? If we increase the resistance of the filter, right? Right now you've got, say, a MERV 8 filter, right? It doesn't have a lot of resistance, and that's important because the fans need to move a lot of air. You increase the resistance of the filter, you're moving less air. But we've shown that those coils are so large that we can move less air. and still satisfy temperatures. So that's great. So we could put a MERV 16 filter in there. And that's got a lot of resistance.
13 would be fine.
What's up?
13 would be
13
fine.
would be fine. I'm just picking a number. But you could have one with higher resistance and get more filtration. One difference, depending on how we control these things, because we didn't really work into the details of the unit ventilator, the future unit ventilator controls, partly because Rupert's, like, I feel like you've got that. And, you know, one way to approach that would be if there's no call from the thermostat, the fan can actually shut off because there's no ventilation required.
It's already being met by the roof.
Yeah, so when your ventilation is taken care of and the thermostat's satisfied, valve closes, the fan turns off, everything gets really quiet.
It would be like a residential unit, basically, be on demand.
Now, if we get the water temperature exactly right, that's not gonna happen very much because it's always gonna just keep up with the. But nothing's perfect, right? So there's a reasonable chance that the fans are actually quiet. And one approach is to actually, whatever speed they're on, turn it down to a lower speed. Because now it's quieter, but now, of course, we've got less resistance that we're capable of overcoming. So there's a trade-off between filtration and noise. And I would suggest, I don't know this, but I would suggest that I would rather do the air quality with the big ventilators on the roof and keep the filtration at the MERV 8, get the noise benefit instead.
That's 8%.
But it's a trade-off, and if you had people complaining about pollens or you know, there are things you could bump them up. Then the question is like, is measuring the air, deciding which thing is in that classroom.
I feel like I've been hogging all the questions. I'm running out, so somebody else is gonna need to jump in here.
Folks.
Yeah, I've got a question on phasing, unless there's someone else from the school or the town. I'd rather have the school or town asking questions.
Chris, I have some, but you go ahead.
Yeah, if you're going back to the phasing, towards the end, yeah, right there, perhaps. So step 2, you're sealing off the unit ventilators. But I don't see where you've added new ventilation yet. Am I wrong there?
That is the very first thing, is
Oh,
rooftop.
it is, okay. So you're adding the new ductwork
And rooftop units.
and rooftop and place rooftop units. Okay, gotcha. All right.
It's all one, all
Yep.
one. The upside is you have cooling, right? It may not be
Yep.
all the cooling you'd ever possibly want, but for probably almost all of the school days, you have plenty of capacity just with the ventilation based.
Got you. Okay. And step number 3, adding the modular chillers, that's adding both heat and cooling?
Correct. That's the electrification or the full electrification component. And it adds sensible cooling.
Gotcha. Okay, great.
John?
Most of my questions are like me making sure I understand as opposed to, and some things about how to talk to folks in town about this.
Mhm.
So the hot water. I know that you're basically you're getting that hot water from the chiller from the front. So you're actually integrating the hot water service with the building.
Yes.
Okay, cool. So we can remove that resistance here.
Yes.
Okay.
Or use the existing tank if it's in great.
Sure, yeah.
You could do a plate heat exchanger. There's lots of ways.
Yeah, and then I think I get this, but again, just because I'm not a building expert.
Yeah.
You're using the existing heating system as a heating and cooling system
Yes.
with the air to water heat pump,
Yes.
and then blocking off the exhaust component of the current ventilation system and adding
And the intake.
and
The
the
current
whole thing.
intakes are blocked off.
Got it.
right? The current exhaust pathway moves from exhaust fan, where you just throw it all away, to the rooftop
I see.
units, where
Yeah.
you can recover the
Right.
energy.
And then adding new fresh air, basically.
Right.
Got it.
Although there are, as Oliver pointed out, there are some places where the existing ductwork exists, so you can use that for your fresh air ducts.
Yeah.
And just build off of it.
The air sealing can happen whenever, that's independent.
Yes.
The roof insulation would have to happen when you do the roof.
Not have to. Would be
But it would
cheaper
be a
to-
better-
It would be a
yeah,
better, it would be
yeah.
better to coordinate it, but as Rupert pointed out, when we were on the roof, and he was pointing out that it's not that hard to.
Yeah.
John, the roof insulation would have to happen when we change the
Surface.
surface.
Yeah, when you redo, yeah. Yeah,
But
no,
it
but
would-
that's independent of the rest of this project, potentially. If we.
Potentially.
Right, I get the idea of doing it all at once makes a lot of sense. I'm just thinking through like, we got money for something.
Yeah.
And not everything. How to, those are trade-offs, right? Okay, and then,
Membrane, that's the word I was thinking.
Yeah. right, so two other questions. Which I think you even have potentially a slide that speaks to, why not other electrification technologies, both geothermal and also air source, air to air?
Well, so this does have air. This is mixed.
I see, yeah, right, on the roof,
The
yeah,
rooftop ones are air source.
Yeah.
To air,
yeah,
and then the water source one uses your existing distribution system.
right.
I'll answer the second question, but I think, was it Oliver, this was yours about the geothermal?
Yeah,
Or, yeah, I'll let them answer that.
So, geothermal is kind of the big, like, buzzword. A lot of people are talking about it. It's a big thing now. But there's a few reasons why we didn't think that was the best idea. So, first thing, it's really expensive. Millions and millions of dollars to drill geothermal wells. You probably have the space for it, you have the big field out back, which is really great. But part of the issue is that because you have such high heating loads as compared to your cooling, what can happen over time is your system can become unbalanced, and your overall efficiency can decrease.
Yeah.
Because, in the summer, you're cooling down, not heating up that ground, and then in the winter, you're basically pulling that heat back out of the ground. But if that exchange is unbalanced, then your efficiency will greatly decrease over time. And as we saw in the efficiency graphs, there's a lot of times where when the air temperature is at a certain point, it's actually more efficient than geothermal will be, because you have a constant ground temperature. But if air is only, say you're only heating up the air by 10 degrees, you actually have a higher coefficient of performance than you would with the geothermal system. So it just didn't make a lot of sense to us.
That, the main one really is the thermal imbalance.
Yeah, that makes a lot of sense. You're not
actually-
using the building when you're not gonna be able to return.
You end up freezing. What we have is lots of examples of actually frozen
Under
geoexchangers, where you first, they'll start adding glycol to their system, because they now are with frozen ground, and you're building permafrost, is what you're doing. And eventually you have a system that just doesn't work.
Yeah.
We need something that should work for our use.
Two other questions, which are more about how to communicate. So the first is, you had the ballpark cost, 1.6 million, I think. What would replace of existing tech with conventional
yeah.
look like even bulk, again, it doesn't need to be exact apples to apples.
Well, I mean, you currently only have cooling, right? What's that? Well, yeah, I was gonna say in the
Right.
office.
Yeah. Yeah.
So, I mean, what you're getting
Oh, I get
is-
that.
Is not.
You're getting a much,
it's-
much.
You're
more
not getting
capable-
the same thing, which.
Right.
The truth is, I mean, tell me if I'm wrong, but most of the people in the school do not care how it's heated.
Right,
They just don't want to be uncomfortable.
yes.
So really, you know, for the for like replacement, well, actually, I can say that I was recently involved with a boiler replacement. It's a gas boiler, not oil, but you know, whatever, similar size. And that was almost,
Mhm.
not quite, I think it was like 800 something or other.
Yep.
But you know, it's not insignificant, and in this case, if you're actually removing this boiler, which I don't think we saw any evidence that we needed.
It's in good shape, but
Yeah.
I mean, I would expect the boiler to run 25 years old, more or less. It's on my radar.
Yeah, my impression is that you've actually been managing this boiler so well. Like, if you don't have short cycling, if you know, so it's not the age of the boiler, it's the number of cycles that kill it. And, you know, so actually, the boiler that I'm talking about that I was involved with replacing was so heavily short cycling that it was only, it was, we replaced a boiler that was only 12 years old. And it's because it was massively oversized. Now, this one's oversized too, but not by the same degree. And probably based on how it's got set up, it's not, you don't have those sites. Anyway, the main thing is replacing that would mean removal is actually hard. You'd actually disassemble it, take it apart. So that removal cost. This says leave it in place, use it if you need it. Hopefully you don't. So the overall cost, is probably comparable, but a bit lower than the DOS units.
Yeah.
The DOS units are giving you something you don't get.
Right.
Which is filtered air, energy savings, or whatever that word, and cooling. And mainly the thing we heard from a teacher was like, cool.
Yeah.
We need cool.
It's not getting any cooler.
Yeah, so, or anywhere else.
Yeah.
In terms of the lifespan of the building equipment, you know, we are looking at, you know, potential end of life for all of the HVAC stuff. It's all the same age, but
Right.
all part of the big.
Right, all the, yeah, right, that's a good point. So it's not just replacing the boiler, it's replacing all that stuff.
Right, now what this assumes, which is a fine assumption to make, is the boiler is gonna continue to work. We don't need to worry about, it. We're gonna reduce its load, we'll need to exercise it, but that might prolong its life. We're gonna assume that the water pumping system continue to function just fine.
Yeah.
I mean, eventually those pumps will have to be replaced.
I would say there's a pretty reasonable chance that when you add these air to water heat pump modules, you might at that point consider replacing pumps. Because depending on the exact plumbing design, you might change the logic for how you want those pumps to operate. And now you have variable speed pumps that can be controlled by pressure or temperature. And our typical approach is to control them by pressure. But with essentially the heat exchanger in these the chillers, you want ideally to have, say, 5 degrees Celsius delta T across that heat exchanger. So it turns out that if you can run your main circulator that way, you actually serve all the zones just fine, and you keep the efficiency of your and the cycling, everything on your heat pump, right? So there might be a potential for a pump replacement at that time, or VFD control.
I mean, we have a VFD, but we don't have good pressure controls.
Yeah,
And so that's not in the pumps.
the pumps are honestly, these are some really round.
Yeah, no, that's fine, that's fine. I mean, that's good.
And so the pumps would potentially fit into those round numbers.
Yeah, no, that's good enough, you know,
So if to just sort of finish my,
Mhm.
my litany, the unit ventilators are in okay shape, but they are also aging. The maintenance costs are going up. We have to replace more motors, more damper actuators, more valve actuators. None of this incorporates that. That would just be an ongoing maintenance issue.
Except the damper
We won't
you no
need-
longer need dampers.
Right,
And really, if you wanted to, like, if you wanted to rebuild these unit ventilators as fan coil units cheaper, you could, because we're having such a tight control over the water temperature. You could, in theory, you're gonna hate this. You could, in theory, have the water flow freely, have no valve to to change the water flow. And simply operate the fan part
Mhm.
based on to air temperature demand.
Right.
So there's an entire valve you just don't care about.
Yeah.
And so now you've got an aquastat potentially, or sorry, not an aquastat, because you took away the valve,
that's just
a
a relay.
thermostat,
Yeah.
or a relay operating your fans.
Yeah.
So it's possible to, and reusing coils, again, as long as you've kind of kept things in good shape, they can last an incredibly long.
It's the moving part.
Yeah.
Yep.
So, but just, I'm sort of still trying to answer your question of how does this compare to a total redo? And this isn't replace all the equipment, so it's hard or even to compare to total.
yeah. But the thing I was missing that you said that I think is quite useful, is like, it's not like everybody, at least in town, is like, oh, new boiler, right? But it's not just new boiler. It's air handlers, it's all this other stuff. So if you're saying boilers 800K, air handlers are plus that.
Yeah.
So we're actually not, you know, the big question is how much more is the premium of going to a clean building? And I get that we get all these other benefits with that.
Yeah.
But like, you know, if we get all these extra benefits and a clean electrified building for like 400K, 500K, that's a pretty useful
One
proposition.
of these DOAS units is your gym unit,
Yeah,
and that one seems like it has potential to be on the decline.
yeah,
So to this discussion, I'll add that the high efficiency system can garner grants, green community grants. And if you're going to work with MSBA, they are no longer providing funds for any kind of fossil fuel burning system. So even if you're going to work with them to upgrade your system, they're going to be pushing you to a heat pump as well. And the last thing is that, you know, if you're going to spend a bunch of money, whether it's to redo the current system or put in a new system, it's really nice at the end of the day to actually have a better system than what you had before. So to spend all this money and end up with the same system that you had before, with the same flaws you had before, is a little kind of like, too bad, you know? So.
I'm totally with you, Chris. I'm thinking of, you know, the years of conversations to come and how to make the case. And that is all, you know, beyond that, just, this is how we get money from the state, like, you know, like what else do we get? And like, this is really, really helpful.
No, I hear you. I hear that's exactly what you're trying to say. So I'm just tossing a few thoughts in on that. Yep.
I guess one other question is like, do we need the boiler? Because I know some, I mean, Chris can speak to this, but I know some state, at least on the residential side, you get more money if you go completely electric with no backup, right? Like, and so I don't know if that's a prerequisite in the commercial or educational space. Yeah. Just asking the question.
We sized it so that you don't need them,
Yeah,
but the electrical grid can go out.
sure.
And if you have a generator and all you need to operate is a pump
And an oil well.
and an oil, pump, you know, but you don't have to operate a bunch of heat pumps.
To keep them tight to freeze.
Yeah, you can, that generator is probably burning a fossil fuel. And we're only talking about probably a few hours, maybe a day of operating. Again, you know, like it's not, you would, it's not that it's a different principle than the one that is often the case where we say heat pumps lose efficiency so much down at
Sure,
very
no,
low
yeah,
temperature
yeah.
that we're,
There's no actual load
yeah, below,
allocated.
below 10 degrees, below 15 degrees, whatever, we're gonna switch over. And there's a pretty decent logic to that. That's actually pretty logical. But we didn't design that.
Yeah, Yeah.
This is backup. Or if the temperature really does get below -5 degrees and you need to maintain an occupied set point temperature, pretty unlikely, those two things happening at the same. Then you could find a situation where the boiler would have to come kick in because we didn't give you.
Yeah. I guess just one weird little town quirk is, so there is a generator on site. It's there to service the community center and the elementary school shouldn't, but public safety would come first, which is police and fire.
Yeah.
So I actually don't know if that generator could do both. Right? Like
No,
it's,
we haven't changed the load. If the generator is there for emergencies, in emergencies, you don't try to run your heat pumps.
no, I understand that. What I'm saying is, I actually don't even know if today
Oh,
that generator can service both
Oh.
buildings. And so there's a world here where that scenario you just said about having the generator available to run an oil system might actually not be, if the community center's out too, which presumably it would be.
Yeah.
We may need, priorities, police and fire, right? Like, so I guess that raises a different question, which is with the air sealing and the new insulation, do you guys have a sense of like, how long could you go before you're in negative temperatures inside the building?
So
And that might be a hard question. But
it
just
is
ballpark.
a question that we could answer with the model that we built. But we didn't.
Yeah, I mean,
And
it's an extreme question.
It's not really, so we could run that model. We could create some cold temperature scenario. So here we've got a situation. Are we talking about the power goes out and it's the coldest hour ever?
Yeah.
Pretty unlikely that those two
Right.
things coincide. So like, what's the outdoor temperature when we are having a power outage? Which risk or which level of risk are you interested in? I could say that if it's average temperature, so around freezing. A building like that with the ventilation turned off.
Yeah.
Right, so it's not occupied. Right? Ventilation is turned off and you have the thermal mass of the building and reasonable-ish insulation for the time and all that. You are unlikely to have any frozen pipes unless this thing lasts for like 4 days.
Mhm.
Unless, of course, you've got that one pipe that's in a exposed place.
Yeah.
So the current situation we have is that the hydronic piping is plugged because it's getting direct outside air in every unit.
Right.
And so that gives us some insurance. The potable water system, obviously,
That's
is,
the one.
and so that's the one that we would be considering. I mean, we should talk about getting rid of the glycol, because it's a less efficient transfer medium, but I'm not sure that there's much gain.
And actually, if you get to these chillers, you're actually sending that water, the most efficient, cheapest way to do it is to send the water out there, don't have a heat exchanger. So you end up needing glycol anyway.
Because we're sending water.
So you end up with keeping glycol in your system. There are things you can do with if you're really concerned about the domestic water pipes, which obviously are not, freeze protected. One is to actually investigate where they go. Carefully analyze where they go. If they're in the middle of the building, they're probably fine. If they're running off the edge and the air sealing may save them. So I can give you examples of places where the pipe is going right up near the ceiling and we did this perimeter air sealing thing. And that solved the problem that was causing the school to never go into unoccupied mode because they were so terrified of freezing pipes and all. It's like, but that's not the school.
We also have a sprinkler system.
Okay, yeah. So, I mean, the main thing is to not let the temperature get too low. I would say the real answer to this is we want to have the ability to use that generator to operate our pumps. And to, you know,
Even if for a couple hours a day.
yeah, even a little bit. And so now it's a question of, let us look at the police,
Sure, we could, yeah.
and try to control those loads. And just trade things back.
No, that's, and then I guess the last question I have is, you've done this for lots of towns and lots of buildings, so what's the logical next step for us with this information? Like, I mean, obviously, there's a more rigorous design step, and then, if we had the money in hand, which, we'd be going out to bid and doing all this other thing, but like, what, in your experience, it's like, what's the next step?
I mean, Chris is probably part of your next logical step.
Yeah.
Yeah, I mean, that's it. Getting the grant funding, coordinating with, I've already forgotten which utility.
Eversource.
It is I'm sorry to hear that. But
National Grid actually better, like
they seem to be, but getting the incentive, so Eversource will subsidize the ERV component. But they do have incentives for heat pumps, although this might be a special one, but so getting them on board.
Yeah.
Explaining it, and getting an incentive described so that you can build that into your Green Communities grant. Chris can give you more of the details, but I think you only get the one electrification grant and you have to give up your next Green Community grant or something like that. But I would think that an electrification grant, which gives you 500K, would be part of this.
So I'll have some thoughts. There's kind of two pieces. Some of this is complicated enough that you're going to want to go out and get a design for it. Other parts, the weatherization, the air sealing that you're talking about, you probably could do through the program expediter process. You probably come in kind of a typical Green Communities grant. What Ben was talking about is that there's an option to get $500,000 if you're really trying to decarbonize. And he's right, you then can't go back for another bite of the apple for 2 more years. So it's basically a 3-year cycle instead of a 1-year cycle. If you're going for that. You, at the very beginning of your slide, you talked about some of your goals, including net zero, and it looked at climate leader communities. So if Pelham is looking at becoming a climate leader, designated climate leader community, then there are going to be larger grants coming through that program. They're not defined yet, but they're being talked about as fairly large, over 700,000 type grants. So that's another possibility for grant funds. You should absolutely get the utility involved from the very beginning. An early conversation off what you're trying to do, but then as you get more complicated, where you need some design engineer in there, make sure that they're working with the utility. And I'd advise possibly to even have Ben involved, because we know that there are design firms that just don't get some of the things that Ben often puts out there. So you're going to want to find a design firm that is willing to work with the ideas that Ben's putting forward. So order of opportunity, the low-hanging fruit, the ones that you can do fairly easily with Program Expediter. You don't need a really in-depth design. That's kind of like an early thing to do. To get designs, you could look at a municipal energy technical assistance grant to help with that. At the moment, what are we, 1250 or is it 15,000 now? Not gonna be enough to cover a design completely, but it can help you for that. So just you start getting some designs in place right up front. I think Ben's already given you enough to start working it into your capital improvements plans. It sounds like you're gonna be doing a re-roofing of the building.
Yeah.
So, and I think Ben has given you a lot of ideas on how to make sure you do that right. So you're building in what you need in that re-roofing so that you're ready to put equipment up there when you get to it. That's an important phasing. I think Ben's helping you out with that. Those are some thoughts. Any questions?
Nope, that all makes sense.
So, Chris, my impression right now is that MSBA is got a huge backlog of what's called accelerated repair projects like roofing.
Mhm.
And for roofing, we've been applying for the middle school roof here at Amherst, every year for the last 5 years. And they never have the money. They didn't even take applications last year. So it looks like they're really barely able to cover 30-year-old roofs.
Hmm.
That will end up kicking the re-roofing project out into the 2030s.
Oh, yeah.
So, that's part of why I was trying to get a handle on the importance and the significance of the added insulation. It could well be that, you know, in their infinite wisdom, the legislature will find some other funding sources. For
Yeah.
the number of school buildings that are all, were built for the baby boom and are now needing serious work. Or they may not.
You know, a thing to think about, if that's the case with the roof, now I'm understanding. So it's useful that we did not consider roof insulation because we're not gonna get it for a long time. Two, that means that we're talking about actually cutting the curbs, you know, making your penetrations potentially before you do the roof. And then as you re-roof, potentially having to remove the equipment. Unless you build those curbs with the assumed height of the future roof. And set it up so that you maybe don't have to re-roof. The other thing is, there's more than one way to re-roof. And so this membrane, let's say we've got an issue is with the membrane. It might be that patching the membrane is good, but the problem is it keeps on getting exposed. You know, and so you can change the design of the roof from a membrane on top, which is what we have, which is fully exposed, to a ballasted roof, where you basically patch your existing membrane, add some insulation on top of that, and add some ballast. And that can potentially be lower cost and allows you to kind of not care about the order.
The other thing I'll add to the conversation, is that, going through the MSBA, they're gonna fund a big chunk of the roof, but they're gonna add a bunch of layers that increase the overall cost as well. Well, so my understanding, and, you know, anybody that knows more about this, I hope you'll correct me, but my understanding is that, we come up with a design, then MSBA says, okay, we need to have an independent designer design it. So basically, you're doing design twice, and they require a separate layer for project management. Which if you have a roofing company that you can trust, you might not need quite that much overhead. So I think it's still a net gain using the MSBA, but there are towns that couldn't wait and had to pay for it themselves. I think Leverett recently had to do that. Suspect that it lowered their overall costs, but it wasn't like having to pay full boat without the MSBA. They were able to cut some corners, and that's the tricky part, you know, is how do you decide which corners to cut?
I guess one other roof question, there's been talk, and we did actually get a design done of rooftop solar on the school. that kind of ballast roof idea, would that eliminate solar as an option?
No,
Okay.
because your mount is actually ballast.
Yeah, no, I mean, the solar project would be, the idea was to have a ballast, not.
Yeah.
So that,
But there would be less roof area available. because
yeah.
The ductwork is inevitably gonna have to be above the roof where it can't be below the deck.
Yeah, there may be some of that, although
This project would reduce the available space.
it would.
Yeah, and which is,
Although,
I mean,
if
you
you
know,
look at how, depending on what you've got available in the plenum, I mean, I gotta give these guys credit, because I did not figure, well, I didn't figure out the routes. That they were really careful about how they routed these, especially the exhaust ducts.
I can't wait to study that drawing close up.
Yeah, that's the thing. Once you do, you'll be like, oh, actually, that's mostly not above.
The inside, the envelope.
Yeah. And that is better than, like, I assumed what you would assume. But nonetheless,
sure, I mean, it's good to know.
additional unit here
Sure.
that removes some rooftop area. You have other areas that, where ground mounts might actually be in terms of cost.
Yeah.
Any other,
Has there been a study done on roof loads to be able to handle any added air handling units or PV?
When the energy committee at Pelham commissioned a design for a rooftop PV, that was done with structural engineering in mind. And so that was done, but I don't know how that raises there's a space question and a weight question with these new units that we would probably have to revisit. If we go to pursue solar, we probably want to be double checking the roof load.
if you're doing both, yeah, that
Yeah.
there's potential, or you might find locations where you
Thought you could, now you
You
can't.
really can't.
Yeah.
But it's nice to know that you've already taken a look at it for PV, and at least for that, you're not facing a situation where it says, no, the building can't handle this.
Correct. No, I mean, we
That's
were
good.
actually surprised. It was like 3/4 of the roof area was in play. Wait, from a load perspective previously, and then, again, it sounds like that might shrink a bit, but even then, you'd still have a project that's pretty big.
Nice, okay.
Any other questions or issues? Margaret, do you have anything that you need to? Thank you guys very much for coming, and thank you, team, for really an excellent job.
Yeah, I want to thank all of you. Thanks, John, for getting this to happen.
Yeah.
And thanks, Ben, for
I,
steering.
I do have one question. Is this recording going to be available somewhere?
Yes, it is recording, and I guess I have to talk with Lauren about how we post it, but I think probably we'll make a YouTube video of it and post it somewhere.
Yeah, we'll be in touch with the slides and the recording.
Great, thank you.
Yeah, well, thank you very much. Bye.
Everybody.
Great work, everybody.